for paper 2, question 12. In fact, when there used to be 2 papers. So 12a, 7 students measure the distance L with a tape measure. The results are as follows. So a bank of results, whenever you've got a bank of results, they're always going to be different because of random uncertainties. So you basically have to calculate what the mean is and what the approximate random uncertainty is within that value. So first of all, the mean is your total divided by n, which is your number of values. And the number of values in this case is 7. If you total all those values up, you'll get 16.807 divided by 7 gives 2.401 meters. The error within that value is your approximate random error, so that's maximum minus minimum divided by the number of values taken. That takes into account, the spread of values that you've got. So your maximum value there is 2.415 and your minimum value is 2.383. N is 7, that gives you 0.00457, or to the same number of significant figures as your answer here, that's 0.005. So you're looking at 2.401 plus or minus 0.005 meters for part A. Part B, the best estimate of the distance x is 91 plus or minus 1 millimeter. Show by calculation whether L or x has the larger percentage error. So percentage errors is just a percentage calculation, calculating how much of the overall value the error is, or what percentage it is, using this equation. So percentage error is the error divided by the value times 100%. L is 0.005 divided by 2.401. You've just calculated what that what the error is in L in part 1 or part A. Times 100 will give you 0.21%. So I should have it times 100 in there. For x, it's 1 divided by 91 times 100 gives 1.1%. So therefore, x has the largest percentage error. You would make some kind of statement there. So x has largest percentage error. So you can start to see that this question is working you through your step-by-step process and uncertainties. It's figuring out what the largest percentage uncertainty is, because you're going to have to use that later on in your final answer. Now C was the tricky part here, because it was using equations that you won't be familiar with. But if you were observant, you would see that you've got everything that you need to know right here. And there's another value that you need up here. So it's all given in the question. If you read the question carefully, then you should have been able to do a C. Calculate the wavelength in nanometers of the laser light, and you must give your answer in the form final value plus or minus error. So part C, we'll shrink this down a wee bit first. So do part C down here. You need to calculate first of all what sine theta is. So sine theta is x over L, which gives 0.091 divided by 2.401, given 0.038. Your value of x is 91 millimeters, so you just converted that into meters. L is 2.401, that's just values that we've been working with already. From there, you need to use lambda equals d sine theta, because remember that lambda is your wavelength. If you calculate what sine theta is, you get d from the question, which is further up. I showed you that a minute ago. So that's 1.693 times 10 to the negative 5 multiplied by 0.038. So that's 6.4334 times 10 to the negative 7 will give 643.3 nanometers. The error is 1.1%, because remember you choose the value that has the largest percentage error, which is this value that you calculated over here, that 1.1%. So 1.1% of what your final answer is, 643.3 nanometers, gives you 7.08. So you make a statement now of what your answer is. It's 643.3 plus or minus 7.08 nanometers. It doesn't have to be expressed in nanometers necessarily. You could express it in meters, or you could express it with scientific notation, as long as your final value here has the same number of significant figures as your error does, then it's all fine there. So you can check that for yourselves. As I said, the equations that you use here and here are equations that you've not been introduced to, but that question is designed to be able to be done by somebody who's never seen those equations before. So if you'd read the question correctly and you've got your values correct from A and B, then it should have been pretty straightforward to figure out what lambda, the wavelength, was. D, suggest an improvement which could be made so that a more accurate estimate of the wavelength could be made. You must use only the same equipment and make the same number of measurements. So we can't do the answer. We can't say, oh, we'll reduce the random error by taking more measurements, because you're not allowed to do that. You're not allowed to take more measurements. So what you've got to look at is, how can you reduce the error in this wavelength? Well, the error in this wavelength comes from it's 1.1%. That 1.1% comes from the error in x, and if you look at the question, x is basically the distance across a screen. So what you need to do is to make x bigger. You need to make that little margin bigger so that the percentage error is not as much of the overall value. So the way you can do that is by moving the screen further away. If you move the screen further away, then you make x bigger. So make x bigger by moving screen further away. Now, that is probably the trickiest part for you at this stage. When we get to the waves unit and we actually look at this stuff, that'll be a bit more obvious. So that was maybe a wee bit taxing for you, but I wanted it to be a difficult question. So make x bigger by moving the screen further away. Some of this stuff will become a bit more clear when we get to that unit, but I thought it was a worthwhile question, considering some people have been struggling with uncertainties. It shows how to calculate the mean, the random uncertainty, how to use the largest percentage error in your final value, and it talks a little bit about improvements to experiments that you might be able to make in order to reduce the error within that.